Okay, let's move on then to number 6. So we've got the statements P, Q, and R. And from those statements we need to write 2 valid conclusions in part A. So I'm going to show you a couple of different approaches to this. Let's first look at a Venn diagram approach. So we've got a set of good mathematics students, and all of these good mathematics students go to good universities. So the students who are good mathematicians, all of them end up going to good universities. And it also says good music students are good mathematics students. So then inside your mathematics students you have your music. All of those music people are good mathematics students, so that set is contained entirely within the math circle. And third, proposition R says students who go to good universities get good jobs. So the universities is in turn contained entirely within the ones who get good jobs. So there's a Venn diagram structure of the situation. We need to write 2 valid conclusions. Well, one possible valid conclusion might be that good music students go to good universities because the good music students are entirely contained within the good universities set. So let's write that one down as a possibility. Okay, so good music students go to good universities. Another one that's entirely contained that we haven't yet discussed is that good music students are entirely within the good job circle. So another possible conclusion would be that good music students get good jobs. And there's a third one still, that we've got the good mathematics students get good jobs. Now you only of course have to include 2 of these 3. Now another approach to this problem might have been to set up some logical statements. So we know that if the person is a good math student, then they go to a good university. So if we could redefine these propositions for a moment, and let's suppose that good math students is proposition P, and good universities could be Q, and maybe good music students is R, and good jobs maybe is S. Yeah, I'm not sure that this is going to end up being a great way of doing things, because we've got 4 different propositions and we've never done a truth table that is 16 rows long. So I won't continue much further than just saying, look, it says if the person is a good math student, then they go to a good university. So we can summarize that by saying that P implies Q. Oops, my good universities was Q and my good mathematics was P. Okay. The second one, we've said that if you're a good music student, then you are a good math student. So that means that R implies P. And then here, students who go to good universities get good jobs, so Q is pointing to S. And one way that you can kind of think about this implies symbol is that it's sort of like a pathway. If R points to P and P points to Q, the end result is that R has pointed to Q. So good music students go to good universities. Alright, furthermore, because we've got P pointing to Q and Q pointing to S, then we have good math students get good jobs. And the last one, we've got the good math students is pointing to, let's think about, oh no, here we go. The R is pointing to the P is pointing to the Q, and the Q is pointing to the S. The end result of all of this then is that R is pointing to S. So good music students get good jobs. So yeah, I didn't want to go through a 16-row truth table, but when you've got a series of implications and things are implying one another, that's a conclusion that you can draw. Alright, part B. Write in words in the following, each of the following. So we're taking not Q. Let me just remember what P, Q, and R was. So not Q. So good music students are not good math students. And P, this is looks like an A, doesn't capital A, so it's P and R. So proposition P was originally good math students go to good universities, and students who go to good universities get good jobs. Alright, so let's write that down. Good math students go to good universities, and proposition R, students who go to good universities good universities get good jobs. Alright, number 7. Alright, if each of these compound propositions is true, what conclusions can be made? So we've been told that this thing right here is true. So imagine, what are the numbers that are less than 7 or are greater than or equal to 3? Now, or, when we're thinking on a Venn diagram, just means shade both. We shade all of A, or B, and we shade all of B, right? And it's the same thing on a number line. The or means that we're going to shade both sections. So we'll shade the region x is less than 7. So we shaded everything less than 7. Or x is greater than or equal to 3. So equal to and greater than. Oh look, we've actually gone through the place that was previously an open circle, and we've shaded the entire number line. So this statement isn't actually really very useful. This tells us that we're dealing with all real numbers. And at the same time, x is not less than 7. If x is not less than 7, that means that x is greater than or equal to 7, right? So we've got all reals and x is greater than or equal to 7. Alright, let's remember and. And in a Venn diagram is the region of overlap, the region that is contained in both at the same time. It's the same thing when you're shading on a number line. Okay? We need to look for the region of overlap. So my first condition was the all reals. I'm just going to graph the all reals situation above the number line temporarily so I can find the region of overlap. And then I've got my condition x is greater than or equal to 7. So here's 7. And it's greater than or equal to. What is the region of overlap between these two things that are connected by the and? Clearly, they were only overlapping from here and upwards. Now, looking at my number line, it's quite apparent then that my end result is x is greater than or equal to 7. But I haven't really used a logic approach here at all, have I? So I'm now going to show you how you could do this by logic. Let's suppose that x is less than 7 is proposition P. X greater than or equal to 3 is proposition Q. This is, I hope you can notice, it's not P, isn't it? So let's set up a little truth table. P, Q, and then we've got not P. So P is true, true, false, false, true, false, true, false, 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 true, true. So, let's think about what I want to do here. Oh, I see. I forgot to forgot the column beforehand. Let's just start that again. So I've got then P or Q, and then I've got the not P. So P or Q, this is going to be true, 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 false. So says our truth table down here, true, 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 false. And the not P, false, false, true, true. the opposite of column P. And now I need to take the and, the conjunction of these two columns, and we know that in a conjunction it's only going to be true if both sides of the conjunction are true. In any other case it's false. So we've got then P or Q and not P. So let's see, true or false, no that's false. True or false, no that's false. True or true, that's true. False or true, okay. So the only time it's true is here. So when does this true outcome occur? When do we get a true outcome? What can we learn? Okay, well that happens on the third row. It happens when proposition P is false, but proposition Q is true. So if proposition Q is true, that means that x is greater than or equal to 7. And if proposition P is false, that means that I don't have all reals. And that indeed is the case. I have only x is greater than or equal to 7. So in fact we could actually put in some test values for x that meet these conditions. If P is true, so x is greater than 7, and Q is true, so at the same time x is greater than or equal to 3, well, if both of these things are true at the same time, then clearly x is in between 3 and 7. If P is true, so x is less than 7, but Q is false, x is not bigger than or equal to 3, well that must mean then that of all of the values we've got that are less than 7, we don't want the ones that are bigger than or equal to 3, so we're dealing with only values that are less than 3. Let's suppose P is false, so x is greater than or equal to 7, and Q is true, so that means that x is greater than or equal to 3. Well, if x is greater than or equal to 7, of course x will be greater than 3. So Q will be automatically true if P is true. And so these are the numbers where x is greater than or equal to 7. And this is really the row that we want, isn't it? Because this is the one that gives us the true outcome. And so we can only conclude, the only time we get a true outcome from everything is when our x is greater than or equal to 7. Now it turns out we didn't actually even need to think about this fourth row, although we could have tried, because we're told that each of the following compound propositions is true. So, I mean, that kind of gives us a clue, doesn't it, that we know that we're in one of these top three because we know that the P or Q column must be true, so we can cross out the fourth row straight away. And then we also know that this is true, not P is true, which means P must be false. So we can cross out these two rows, because in those ones P was true. So that's another way you can see that we end up with only the third row, and the only values of x that work in the third row are x greater than or equal to 7. Let's do part B. P is equal to 3 if and only if Q is equal to 5. If I write that down in symbols, P and Q are equivalent. That's the if and only if. We're also told that if Q is not equal to 5, meaning that is the not Q, then R is not equal to 12. Let's call that not R. Okay? So I'm defining my propositions here as P is the proposition P is equal to 3, Q is equal to 5, R is that R is equal to 12. So let's see what we can conclude from all of this. Alright, let's reason this out first, just by thinking about what this equivalent symbol means. And remember that we're told that each of the following compound propositions is true, and our compound proposition here is P if and only if Q. So if we know it's true, then we must be here or here. And in those two situations, P and Q are the same as each other. So, either these things are both true, or they are both false. Those are the two ways that this particular proposition can be true. They're both true, or they're both false. Okay, so whenever this is true, this must be true. Whenever this is true, this must be true. And vice versa. Now we're then told that, in fact, Q is false. And we know that whenever Q is false, P is false. So then, we can conclude that we can replace the Q is not 5 with its equivalent statement that P is not equal to 3. And so we end up then with if P is not equal to 3, I'm just replacing it, then r is not equal to 12. Now some other neat things that you can draw out of this, though, involve the contrapositive. Because not q implying not r, you might remember, is logically equivalent to its contrapositive, which becomes r is if r then q. We switch the sides of the symbols and we negate them both. So you could have in fact said if r then q. So we could say then if r is equal to 12, then q is equal to 5, which we know that we are replacing with the p is equal to 3, thanks to our if and only if statement earlier on. I don't really have the room nor the time nor desire to make an 8-row truth table here with p's, q's, and r's. But that's another way that we could have done this, when we would have been using only the rows in which p and q are both true or both false. That immediately cuts down to only 4 of the 8 rows. And then we would have cut it down. If this is true, then we can get rid of a couple of falses, and that cuts it down to only 2 rows. And then you'd see probably that we end up with rows that imply this conclusion or this conclusion. It's contrapositive. Okay. Number 8. So the following truth table contains 2 entries which are incorrect, one in column 3 and one in column 4. You would never ever get this question anymore, because of course they give you the truth tables. We can see that p and q is only true at the top, but here they've got it being true at the top and the bottom. That one is clearly wrong. And column 4 is is not p, and of course they give you the not p column now. False, false, true, true, false, false, true. This one is the one that's incorrect. Now we have to fill in p or q. Again, you wouldn't get this question anymore on IB. It's an old question because you now get given the truth tables. Clearly it's true, 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 false. And then you can confirm this if you like, but if we combine the p or q here, we combine it with an and with these ones, you'll end up with false, 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 false. IB won't lie to you about that. So we filled in the 2 missing values in column 5. It says, which of the following words would you use to describe the statement in column 6? Because it was false, 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 false everywhere, is called a logical contradiction. If it had been true, 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 that would have been a tautology. And the converse, inverse, and contrapositive, while they are important words in the logic unit, they have nothing to do with all truths or all falses in the truth table. They sort of are talking about flipping the sides of an implies, an if-then statement, and possibly negating them. And we know that the inverse and the converse are logically equivalent, and the original statement and its contrapositive are logically equivalent. Number 9. Let's write in words the proposition P or Q with the symbol on the bottom, which means but not both. So Danny goes to the cinema, or Danny studies for the test. But not both. Part B, given the statement says if Danny goes to the cinema, then Danny does not study for the test. So if Danny goes to the cinema, that's P, then Danny does not study for the test, that is not Q. Part I, write in symbolic form the contrapositive of the statement that you just wrote. We know that the contrapositive, we switch the P and the Q around, and now we're going to negate both of them as well. The negation of not Q would be positive Q. The negation of positive Q would be negation of Q, P. Not P. There's the contrapositive in symbolic form. And the last question, number 10. So there are your statements P and Q. We need to write down in words the inverse of that given statement. If you watch the music TV channel, then you like music. The inverse is just going to negate both sides of things. So if you do not watch the music TV channel, you just got to memorize inverse, converse, and contrapositive. It's the kind of thing that you just look over right before an assessment, and put it into your short-term memory. Then you do not like music. Let's make sure that we negate both sides. Write down in words the converse of the statement. Alright, the converse, we're just going to switch the order, but keep them as positive. So, if you like music, then you watch the music TV channel. Alright, we now need to construct truth tables for the following statements. So let's do it all in one big truth table. We've got P and Q, and then we've got P implies Q. This is too easy now that you're given truth tables in the formula package. We're going to need to know what the not P and the not Q are before we can find out what not P pointing to not Q. And then we need to find out what P or not Q is. And lastly, we need to find out what not P and Q is. Okay, so big truth table coming. As always, true, true, false, false, true, false, true, false. P pointing to Q, we know is T, F, T, T. Not P, F, F, T, T. Not Q, F, T, F, T. Not P pointing to not Q. So we know that this is only going to be false if T is pointing to F, and that only happens here. That is going to be false. Everything else is true. Nowhere else is T pointing to F. Then we've got P or not Q. So there's my P column at the beginning, and here's the not Q column. And so let's find out when both of them or one of them is true, right? In an or situation, the only time it's ever going to be false is if both P and Q are false. So anyway, so in P and not Q, when are they both false? That only occurs on the third row. It's the only time we're going to have a false outcome. The others are all true because we had at least one true or both true. And then we've got not P and Q. So not P and Q. We're now looking at these ones. So let's see, when are they? Now in an AND situation, we need both of them to be true to get a true outcome. So here we've got true and false. No, false and false. True and true. It's on the third row that we are true. And I think everywhere else we have at least one false. So false, false, false. And it says, which of these statements are logically equivalent? Logically equivalent means that they have the same truth table structure. So let's compare the four that we were given. There was that one, there was that one, there was that one, there was that one. And if I compare those four, the ones that are equal are, here they are, this one, TTFT, and this one, TTFT. Therefore, it is statements 2 and 3 which are logically equivalent. And that brings us to the end of the review.